Okay, so I understand. I'm sure you're going to be happy to see me go. Everybody's starting to think right now, we got to get rid of this guy. Holy cow, look at all this. That's only one class. There's this other class we got to talk about. And so, yeah, I mean, it's a shame that there's so much material to cover in such a short time. That's what it is. It is what it is. So, we keep working together and do as best we can. I know that you're a little bit nervous, or at least some of you are a little bit nervous about this course and the way things are going. And I'll just say what I said the other day, which is, in my opinion, I think most of you are probably doing okay. I know right now it seems to you like some of the commands are really confusing. Tim gave by earlier, we were trying to debug his program, and there's a lot of things that seem mysterious, but you'll figure them out. It's kind of like language. Well, it is language. Right? It's just another language. It's like learning any other language. At first it doesn't make any sense. And then slowly you start to recognize the pattern and the logic and the grammar, and it will make more and more sense to you. So one of the things I want to mention, I want to mention just a couple of big ticket things. Okay? I'll call them big ticket things. Okay, I guess we'll write it today. Okay. So a couple of big ticket things. Not necessarily in this order, but they're all important. One is that C++, C++ website that I showed you, it has full documentation. You should always remember that and never hesitate to go and look things up. Right? And as some of you have noticed, you can ask me sometimes about some functions or subroutines. There's not subroutines, that's not the same word C++ uses. But functions, commands, what's the syntax for something like the ifstream command, something like that. Honestly, I don't remember that many of them directly out of my head. But I know they exist, I know where to go look them up. And you should just be prepared to look them up as much as you need to until you remember them. And I think if you never remember them all perfectly, so what? I hear English words, I've been speaking English my entire life. And I still have to look some words up every now and then. I hear the word in English. What is that? So, most English words, though, I've become familiar with because I keep doing it over and over again my whole life. So the same thing will happen with you in computer programming. You'll use some commands over and over and over again, and they'll become completely well known to you. But every once in a while, you'll hear a command that you're not familiar with. No problem. Go look it up. As long as you understand how to do syntax, then you can figure it out. Also, sometimes you'll dream of functions you'd like to accomplish, and you don't know if that command exists. So that's another good reason just to go look. Go look at all those libraries. All right, so some of the commands that he's been using in the notes, and I also used in my notes, to do examples of, for instance, sine function or average. Those are really common functions that probably exist somewhere. You can guess they probably exist. In the last day or two, there was a lot of discussion of group finding. Group finding is incredibly important in engineering. It's hard not to say, it's hard to imagine a good engineering problem that doesn't have some group finding involved in it. Well, because it exists everywhere, there's always a group finding routine. I think in your career, you'll never write a group finding routine. So just because in this class, you've already seen 2 or 3 different ones, you've seen Newton's method, secant method. There's the one in Excel. Has anybody tried that one in Excel? It's called Go Find or Go Value or something like that. I think I wrote it down. Well, anyway, I don't remember the name now. See, I'm making a pointer test. GoalSeek. It's called GoalSeek, S-E-E-K. So even Excel has a built-in group finding routine. My point is, if if you come across a function that you think you need, there's a pretty good chance somebody else already wrote a program that will do it. Right? So the first thing to do is look through the library, one at a time, look at the functions, see if it's out there already. If it's not out there, then you can worry about writing your own function. Okay? So that would be a second main point I would make. A third main point I would make is that the logic of using functions is very, very sound. All right? Now it's becoming less necessary slowly over time because so many other functions already exist. But the main program should just be step by step, kind of the big picture parts of the algorithm. And the real work, as he says in the lecture at one place, the real work of the program should mostly be done in the subroutine. Okay, so you might think of the logic, I don't know, you could think of it like a big company or a big organization, maybe the army or something like that. The main program is like, the big picture commands. Build a road to Hanoi. Build an airport in Da Nang. Whatever they are, the big commands. Each one, then it's followed by a call to a function. Function highway. And that function goes, and it does all the work of building that road. Call airport. That function goes, it actually does the airport. That way, the logic of the main program stays as clean as possible so that you can see what is going on. Also, when you go to debug then, it makes it easier to do it piece by piece. And the debug is the last main point I want to make, but not the least main point. And maybe it's the most important one. The example programs that I've seen for most of you, I think they're missing two things that I've suggested to you should use a lot. And I say it again, that it's really important. I would never write a program without it myself, but I've been doing it much longer than you have. One, comments. Put comments everywhere in your program. Explain in the words exactly what it is you mean to do on the next line. So that when you look at it 1 day later, 1 week later, 1 year later, it's very obvious to you what it is that you meant to do on that line. And the second thing is, lots of output statements, at least in the beginning while you debug it. I think an output statement after every line is not a bad idea. Right? The next line says, n plus equals n. Write n. Right? Make sure it's one bigger than it used to be. If it's not one bigger, then figure out what happened. Okay?
Sometimes in the C++, we find the problem is that when we compile and run it, this comes out with this stop working.
Yeah.
The stop working and why is it?
Yeah, why does it stop? Yeah, some errors are terminal errors, or what's called terminal. Terminal means end. Right? So certain errors are so bad that the program doesn't have any idea. Not any idea. That's not necessarily true. Because sometimes it'll keep executing even if it doesn't really know what it's doing. But sometimes the error is so bad there is no way that it can go forward. Right? It's impossible. Yeah. And so that's syntax, for instance, is one example. So, for instance, if you use one of those open bracket signs, and at the end of that segment, you don't have a closed bracket, when it's trying to compile, it doesn't know where the end of the segment is. Until it knows where the end of that segment is, it can't do anything. So that's a terminal error. But you can have other errors in there, like you meant to say n equals 6, and instead you had n equals 5. So it does do something, but it doesn't do what you intended it to do. And as I said before, I think those are the worst errors. I know when you're trying to run your program, the most frustrating thing is when you get a terminal error and nothing happens. Right? But actually, in the real world, that's not the most frustrating thing. The most frustrating thing is when you calculate 1 plus 1 and the answer is 3. And you can't figure out, if you try to calculate 1 plus 1 and some terminal error happens, then you know you have a problem. But if you try to calculate 1 plus 1 and it says 3, wow. So it's calculating something, but how is it coming up with 3? That's not the right answer. Those are the kind of drive me crazy. And believe me, I've had that kind of thing so often. I talked before, I'll say it again. passing value variables by reference in and out of subroutines or in and out of functions, oh, that can just be a nightmare. You have to be so careful, because you send it down into the function. It has a certain value in the main program. Something happens inside of the function. When it comes back, when the control comes back to the main program, you change something in the function you didn't mean. And now 3 is 4, or something crazy like that. Those are the kind that can really drive you nuts. Okay? Okay, so because there were a lot of questions yesterday about the arrays, I made some notes. I thought I would just mention a few things about the arrays. A lot of his array examples have to do with character variables. He shows over and over again how to put character variables inside of arrays, or make arrays of character variables. There's nothing wrong with using that as an example, but in my opinion, that's not a very common example. I think most people who are trying to do something fancy with words are not writing in C++. C++ is primarily a mathematical programming language. So you can put characters in, you can read words, you can write words, and you can certainly sort things. I mean, you have enough logic already. You could, for instance, read a file that has everybody's name in this class, and then sort them in alphabetical order. You can do that. You can sort them by how long the name is. Put all of the names that are 3 letters, then all of the names that are 4, all the names that are 5. You can do that. You can do lots of different logical things using C++. It's possible, but it's not the normal language that somebody would use to do that kind of thing. Okay. For one thing, Excel. If you really want to manage a lot of data, Excel is usually much better. If you're not making complicated calculations, but you just want to manage data, yeah, Excel is a much better choice. So, for instance, putting everything in alphabetical order in Excel is one mouse click, and you have it in alphabetical order. If you want to reverse it, instead of going A to Z, you go Z to A, one mouse click. So all of those kinds of commands are really simple in Excel. So I think that the Chapter 2 examples on the arrays, 2.11, 2.12, 2.13, I think they're very helpful for learning how to do arrays, but the application he shows is not common. A much more common use of array is the kind I described before, which he also has a few examples of. That's when you've collected a lot of data, and you need to manage that data by making real calculations with the data. Right? Then you use an array because it's so much easier than making up a different name for every variable. Okay? And he gives some examples of doing functions of arrays, and that also is really useful thing to know. The only thing I would say about C++ is MATLAB is set up to do operations on arrays. Okay? So in C++, if I were to take 100 numbers and calculate the sign of those 100 numbers, it's much easier to put them all into one array that has 100 locations, put a for loop, and the for loop goes through 100 times with a counter, and each time the counter is one bigger, and that's the argument of the array variable, and I take the sign. So the first time through, I'm taking the sign of x of 0. Second time through, it's x of 1. Next time through, x of 2. So inside of a for loop, for I from I equals 0 to 99, I can do 100 times the sinusoid, and that goes through this for loop and calls the sign 100 times and calculates the sign of 100 numbers. That's fine in C++. That's a good use of an array in C++. But in MATLAB, if you set up x to have 100 numbers, you can just ask MATLAB sign of x, and it will automatically give you the 100 answers that are the 100 signs. So you don't have to do this. You don't have to keep track of it. So MATLAB is that much more powerful than C++. I've said that already a few times. Okay, any question about the arrays? Let's see, what else did I say? I thought array example 2 in lecture write example 2 in 2.11. Yeah, Alex, you can call that out for one. I thought that was a particularly good example just because something that we've talked about a little bit in here, but if you see examples of it going bad, it's good for you to remember it. And in example number 2, the thing that goes bad is that the size of the array and the amount of data that gets put in there are not the same. Right? So he sets an array to size 8, if I remember correctly, but he only reads 6 numbers. So what gets stored in the spaces for the other 2 numbers? And the answer is, it's unpredictable. Okay? It's unpredictable. So it's very important when you're using an array to be sure that if you intend to use a number, you actually do get it into the right position, or a character variable for that matter. Okay? Any question about that? Another interesting thing about that example is there are 2 numerical values that don't get read, and then he prints them out. And the values that come out are some bunch of digits, e to the minus 300. Well, e to the minus 300, yeah, that's a really small number. But what's interesting is it's not 0. Okay, so it's a round-off error on 0. Right? Why doesn't it just write 0? It doesn't have 0 in that memory location. It's got some number that's not exactly 0. So that's a good example of round-off error. Okay. Another thing I wanted to mention in lecture 212. Lecture 212, there's an example of the getLine command. Does everybody remember getLine? Alex, can you put 212 up? Let's go down to let's try and do this one. Let's get line in there. Oh, use getLine. Okay, yeah. So maybe back up. Yeah, I think this is the example. Maybe back one shows the. Maybe not. Okay, go for it again. Well, anyway, it's not that important, but I wanted to show you something that you can surprise people, especially older people, with your historical knowledge. Okay, so this getLine will enable you to read a whole line at a time, right? And then you can just print it back out. Remember, the normal character arrays in C++, a normal character variable will only hold 1 letter. So it's kind of a nuisance. If you want to read a word that has 10 letters, you need 10 different character variables, like an array with size 10. But getLine is different because getLine will take one entire line and put it into one name, and then you can just print it back out. So what I wanted to point out about getLine is that the size of the line that it reads is 80 characters. Okay, why 80? Anybody remember? I think I said this before. I told you that for years, the way that you put input into a computer was not by a terminal. It's by those cards. They look like little pieces of cardboard, about this big. Those cards have exactly 80 columns. That's how big they were. They were all 80. So all computer programming in the early days was limited at 80 on one line. And so even today now, many, many years later, this get line command is set to a maximum width of 80. Why 80? Because 30 or 40 years ago, or 50 years ago, I don't know when they started, probably 50 years ago. 50 years ago when they first invented those cards, and that was the only way you could put information in something in a computer. Somebody decided that card should be 80 wide. And it's still the maximum here. I think that's kind of interesting. Okay. Any other questions about arrays? There were a few questions last time. Are we all set on arrays? C++ does something with the arguments of the positions of arrays that's different from the other languages. Man, I wish I had a piece of chalk. Sorry. Yeah, no chalk. I've got some in the apartment. I just forgot to bring it. So.
The chalk ran out.
What's that?
The chalk ran out.
Well, there's none in the room. There's some back at my apartment, but I didn't bring it. So I think there's nothing in here unless you see one. Magic. Thanks. Thank you. Okay. Right with you there. Wow. You've been holding out on me all semester. I could have used this all semester. Thank you. So the array in C++, if you set something like x 4 by 4, this array is designed to look like the arguments that go inside of here are x 0 0, right? This is x 1 0 down to x 3 0. This one is x 3 3. This one up here would be x 0 3. Okay? 4 by 4 is a total of 16 places. And if you want to refer to those 16 places, these are the arguments that you have to put in to refer to each place. Alright, so I think by now you should know this, but it's okay if you don't. Now you do. But one of the points I wanted to make is that in Fortran, in MATLAB, in most languages, maybe C++ is the only one, I don't know. A zero position in an array doesn't exist. That's a syntax error. So in these languages, the first position would be 1 1, 1 2, and it would go down to 2 1, 4 1. So when this one says 3 0, this one says 4 1. Where is 2 1 in this one? Yeah, 2 1 would be 3 2, right? So this is 2 1 right here. But 2 1 in this one is over here. So you're gonna be going from C++ to MATLAB soon, maybe tomorrow, and you just remember this, because in MATLAB everything is an array. Everything is treated like an array because it's so helpful, so convenient. So MATLAB just assumes anything you put in there could be an array. And when you call the position in the array in MATLAB, the first position is 1, 1. But in C++, the first position is 0, 0. Okay, so that's a little confusing. That's too bad. Okay. Good. What else? You know, another thing, while we're doing this, we can jump ahead now and do a little bit of MATLAB stuff maybe, but I think we talked a little bit about linear algebra. So if I want to do a multiplication, two arrays. Let's say an array, I'll call the first one X. So it has some size like this, and Y. How do I figure out the size of X times Y? Yeah, let's say this is I by J, I rows and J. So this would be 1, 1. This would be I, 1. This would be 1, J, and this would be I, J. So what size does Y have to be? Yeah, something like J by K. But this dimension, the number of rows here, J, has to be equal to this dimension, the number of columns, right? Where that doesn't work. It's not defined. It's only defined if that's true. So this would be 1, 1, but down to J, 1. And then the multiplication is that you go across this row one at a time and down this column. That one times that one, the next one times the next one, the next one times the next one, until you get to the last one in this row times the last one in this column. Add all those together, and that's the first piece of the product. Now, what size is this? Okay. I equals K. All right. So if you want to multiply two arrays in C++, if you want to do this multiplication in C++, how would you do it? Somewhere near the top of the program, right, when you declare these, you have to declare the size of X and Y. Then somewhere in the middle of the program, you would have nested for loops. The inside for loop would go across here times here. Outside of that one is a for loop that starts with the 1, 1 position. Sorry, this should be Y. Starts with the 1, 1 position of what's going to be the answer. So to calculate, let's call this the answer here. It's going to have a 1, 1. To calculate 1, 1 requires to go across this row that's a total of J times, down this column J times. So I need an inside loop on J, right, that will do that multiplication and add them all together. When I'm done with that, it stores one number of the answer. Then I need a for loop to go, say, across the row and fill in the rest of the row. Then I need another for loop to move down and do each column. Right? So a total of 3 for loops. One inside the next one, inside the next one. That's to do it in C++. Jumping ahead to MATLAB, this command is okay in MATLAB. You just write X times Y to give you the answer. So it saves 3 for loops. A lot of logic. Okay. move on from arrays. Who's got an array question still? Anybody?
What is the to have for loop for the multiplication? The first one is the first one to the first array.
Yeah.
The sub for is the next one and the other one.
Yeah, so you might, you want to go ahead and try to write the commands? Okay, let's get a name for the answer. What do you want to call the answer? X times Y equals Z. How's that? So we'll call this Z. So I'm going to start on, I think I'll start on the inside for loop. Okay? So for J equals 0, because in C++, the first counter is 0, right? If this were in MATLAB or Fortran, you would start at 1. But this one starts at 0. J less than or equal to, now we didn't give it a size, let's put sizes in here. We'll say this is 3 by 4, and this is 4 by 2. So the answer is going to be 3 by 2. Okay? So J less than or equal to, we need it to be a total of 4, but it starts at 0, so we'll do 3. And then J equals J plus plus. Let it go through the 0 the first time. And then we'll say Z of I and K. Plus equals, right? Z of I, K. Oops. Plus equals X of I, J times. And these are squares. Sorry, I'm not using good format. These are square. Add syntax. Good syntax. Okay, that will accumulate that. Now, above this, in each pass, we want to make sure we initialize Z. So I'm going to remember to put up here Z of I, K equals 0. Okay. Then we're going to have another part of the for loop, which will be for, and it doesn't really matter. Oops. It doesn't really matter whether we do the I or the K first. So what we do I. So for I equals to 0, I less than or equal to 2, and I equals I plus plus. And then above that one, we'll put for K equals 0, K less than to 2, so this will be 1. Yeah. And then we're going to need a bracket here and a bracket down here. Okay, and actually this one, sorry, I put this one in the wrong place. This one should go down here too. You probably would want to probably go ahead and do this, just to be on the safe side. Okay. So that logic is not difficult in C++, but it is a lot more work to write this code than to just write x times y. And MATLAB will allow you to just write x times y. MATLAB assumes that everything that you're doing is an array. So you don't have to tell it over and over again which piece of the array you're using, unless you really have to single one out. Single one out. Sometimes you do need to single one out. Okay. Okay, so I think the last thing we looked at last time, we talked about some numerical differentiation, numerical integration. Does anybody have any questions about those two? One thing that I'll point out is that in the examples that are in your notes, for the differentiation, there's discussion of what's called forward. Tiffany, I owe you a piece of chalk. Okay. I've got plenty. I can give you more later. Okay. The numerical differentiation. You can use the so-called forward, central, backward. Now, this is another example of what I would call the art work, not necessarily science, of trying to make a numerical calculation for something that you can't find analytically. So remember that the derivative, this is defined as, analytically, the limit as delta t goes to 0 of x at t plus delta t minus x at t divided by delta t. But let's assume that we had the function. So here's x and here's t. So the idea is to pick the start time t, look at some other point a little distance away, let's say it's delta t. So this point then would be t plus delta t. So this point is x of t. And this would be x of t plus delta t. And so the derivative would be this difference, this vertical difference divided by delta t. So it's this straight line. That's what that calculation would give you for the derivative. Okay, so there's a few things about the art of this that you can't really know in advance. One is, if you change the value of delta t, can you get a better answer? In theory, if you make delta t as small as possible, limit as delta t goes to 0, in theory, if you shrink delta t as small as possible, it should be the most accurate answer. But I know that I described this example from real life before, I'll say it again. Often, if you're calculating a numerical differential like this, it's because you don't have the function in the first place. You don't actually have a function for x. If you had a function for x, you would just take the derivative. What you have instead is a bunch of data for x. So there's a bunch of data points along here. And the data is collected by some device, probably operated by some human. Right? Sometimes that human has a good day, sometimes not such a good day. Some mornings he gets up and his wife yells at him, or he's got a headache because he drank too much beer, or maybe it's just hot, or maybe he's just not a nice guy, maybe he's just a jerk. Right? So who knows? But he collects the data. Instead of getting good data all along the curve, the data is a little bit scattered around. Now, if you only have data and not the function, there's a couple of problems, right? One is, when you get to the end, let me go ahead and erase this stuff out of here. When you get to the last data point, how are you going to calculate the slope at the last data point? Because this method always looks forward. There's no data beyond the next data point. So you can't apply this method. So one idea is to use what's called a central. So instead of picking 2 points side by side, you pick 2 points that bracket the one that you actually want the derivative for. So I assume the derivative at this point will be calculated by taking the difference between these two. Right? Something like that. And the derivative at that point will be calculated by the difference between these two. The derivative at that point is the difference between these two, and so on. Okay? That's called the central difference. What we did before is called the forward difference. The other thing you could do is, instead of having delta t move to the right, you could have it be to the left. So I could decide I'm going to calculate the derivative at this point by looking at these two instead of these two. If I want the derivative here, and I look at these two, that's a forward difference. If I look at these two, that's a backward difference. If I look at these two, that's a central difference. Which one is best? Actually, most of the time you don't know. You don't have any way to know. There's no way that you know, because all you have is data. You don't know what the function is. So if you do a backwards difference, you would estimate that that's the derivative. If you do central difference, that's the derivative. If you do forward difference, that's the derivative. What's the right answer? It's just data. You don't know. You don't know what the right answer is. So that's a real world problem. Now, in theory, analytically, if you make delta t the limit go to 0, it's supposed to give you a more accurate answer. And actually, most of the time in data, if you can shrink this down, these three lines will probably start to converge and look like a single answer. That would be great. But there's this danger in real data, which is you're dividing. So let's say that you let delta t be 0.1, 1/10 of a second between data points. Dividing by 0.1, as we said, that would be the same thing as 10 times x at one point minus x at the other point. If delta t was 0.01, this is 100 times. So what? The problem is that there's an error in this data. What you measured isn't really x. It's x plus some little error. I'll call it error 1. And what you measured here isn't really this x. It's x plus some other little error, error 2. So if I expand inside of this bracket, you get x at t plus delta t minus x at t. This is correct. And then you have plus epsilon 1 minus epsilon 2, the two errors. If this part is not 0, and usually in the real life it's not 0, because there are some errors there. If that's not 0, and you let this time get really small, you're multiplying that error by a huge number. Okay? It's part of the art of engineering. How do you decide? Because the theory says you should let delta t get as small as possible. For the first part of this, that's an excellent idea. That should give you the best derivative. But for the second part of this, it's dangerous. So it's really helpful to have some way to have some idea what kind of errors might be appearing in the thing you're measuring. Now, let me give you an example of the real world. You know that I worked on automatic landing systems for airplanes. When I first started working on the system, it used a radar. It was supposed to work from a range of about 8 kilometers. So the airplane gets out here, and from a distance of about 8 kilometers, we're supposed to be able to bring it in and land it at the right place. And it's being measured by a radar that sits here, that sends out a radio signal, bounces off the airplane, comes back at the speed of light, tells us where the plane is. It only tells us the position at that instant. We have to measure it again an instant later and see where it is. Now we have two positions. It's like 2 points on here. and we'd like to know how fast is the airplane going. So we calculated a numerical derivative to see how fast it's going. What kind of error is in that signal? Well, a lot of real-world measurement devices make the physical measurement using analog. Analog is a continuous signal like voltage or temperature. In the real world, it's completely continuous. It's not discrete. But when you measure it, it has to be converted into a digital number in order to be put into the computer. And that conversion from an analog to a digital signal, that's called an A to D conversion. And analog is completely continuous and unlimited significant figures. But as we know, digital is some limit on significant figures. And it turned out that the digital conversion for that radar, based on an 8-kilometer distance, meant that the smallest digit, remember it's binary, right? This is binary. We saw what a pain in the neck it is to figure out binary. The last digit in here represented about 3 meters. What does that mean? It means if there's a 1 there, it's 3 meters. If there's a 0 there, it's 0 meters. If there's a 1 here and a 0 there, it's 6 meters. It can't be anywhere in between 0 and 3 meters. It can't be anywhere between 3 and 6 meters. It can't be anywhere between 6 and 9 meters. So every one of these errors had the potential. This could be 1.5 meters. This could be 1.5 meters. This one could be positive. This one could be negative. So when I add the two of them together here, the total could be 3 meters. Now, if I turn my radar on and I'm measuring 100 times per second, my estimate of the velocity could be off by 300 meters per second. The plane isn't flying that fast. The actual velocity is not close to 300 meters per second. The error part alone of this could be 300 meters per second. It's completely impossible. Okay? So that's the danger of the numerical differentiation. So I want to mention that I don't have a perfect solution for you because it doesn't exist. Every time that you work with one of these problems in the real world, you have to take into account how you're taking the data. How is this measurement being collected? What kind of device is being used? In this case, it's a radar. It's completely automatic. There's no human. I said a minute ago, maybe you've got a human who's making the measurement and he's not having a good day. In this case, it's not even a human. That's not the problem. I could come in here tomorrow, I could bring a meter stick, and everybody stands on the porch, and one at a time you come in and I give you the meter stick and you measure the distance in this room. I bet no two people would have the exact same measurement. We'd have 40 different measurements. The range of the error, though, should be sort of predictable. If we take all 40 measurements, we could calculate an average. You could calculate a standard deviation. We know from that Gaussian distribution we talked about before, within one standard deviation plus or minus, that's 68% of the measurements. 2 standard deviations plus or minus, 95%. 3 standard deviations, 99.7%. So if I'm trying to figure out what's the worst case, how bad can this really get, maybe 3 standard deviations is useful for me, right? Because that's 99.7% chance that the next measurement should be at least within 3 standard deviations of the average. So I bring you in here and we measure the room one day when it doesn't really matter. From that experiment, I get statistics that are useful for the measuring process. Tomorrow, when we measure something that's really important, I have this statistical measure of what I think the error might be in the measurement. And I can use that to predict how to calculate a standard, how to calculate this difference, so that this thing doesn't blow up with this thing. Okay? Okay. Another thing about that airplane that comes up a lot when you're making a numerical differentiation, that the airplane weighs, depending on what model airplane it is, it might weigh a couple of 100 tons. And as we know, an A380 weighs over 1 million kilograms, right? So that's, I do the algebra, 50,000. Yeah. Okay, so F equals ma. We know that. That airplane can't have a very high acceleration. If it doesn't have a high acceleration, what does that say about velocity? It can't increase very fast, right? It can't get big or small very fast. If the acceleration is the slope of velocity. So if I have the benefit that I know that acceleration can't be very big because this number is so huge, right? M is too big. There's a limit to the F. M is so big, that means A can't be very big. If I know that A can't be very big, which I know about every airplane, they're all big. A380 happens to be the biggest, but they're all big. So if I know that there's not much acceleration, that tells me the velocity is close to constant. So then I can do another trick. I can come in here and I can calculate all of these, and maybe over something like 10 points. Because 10 points, if I'm doing 0.01, 10 of those points is still only 1/10 of a second. The velocity is not going to change very much in 1/10 of a second. So instead of calculating this one time, I calculated 10 times, 10 different pairs, one after another, and take the average. And the idea there is that the average of this error, hopefully, is something like 0. If the device is set up correctly and properly calibrated, the average should be close to 0. So in that case, I can use a small delta t, but then use a lot of data and take an average. Okay? Any other questions? Any questions about this? You know, this shows up a lot. How many of you have active suspension on your car? Yeah, active suspension. Do you know what active suspension is?
That's clear.
Normally a car has... Here's another, I know it looks like a photograph of a car, but really it's just a drawing. Right? It's only a drawing. Normally, between the wheel and the body, there's two things. One, and you know this from 208, there's something that acts like a spring, and there's something that acts like damping. Okay? And these two things put together are the suspension. It's called suspension. The idea of the spring is to try to prevent too much motion, and the idea of the damper is to try to prevent too much velocity. Now, the car's going down a road, and the road's got a lot of bumps in it. So what's supposed to happen is that the wheel goes up and down a lot, and the car doesn't move very much. So if you're sitting in the car, you don't notice the bumps. That's what's supposed to happen. Right? Now, as you know, from 208, well, I guess you know, did you calculate natural frequency from 208? Did you hear about this?
The spring?
Of anything, natural frequency for anything. What's the idea of natural frequency?
It's inverse of the time operation expression.
Yeah, something like that. The inverse of the time for each oscillation. Okay, so if I take that suspension system, let's say I put it into an experiment. I've done this. This is another big project I worked on. It was with one of the major car manufacturers. I won't say the name, but their system for testing this cost $100 million. So they think this is very important. Right? They can take what they call a quarter of a car, one wheel at a time, and at the top of the suspension system they have an input. It's a motion input. Not force, motion. And down here they measure force. For the motion, a regular road looks random, or it looks like some random bumps. But actually, if you expand this, you can always write it as a sine series. Right? So any x of t can be written as a series that looks like x at 0 plus a sum of a bunch of sines. This goes to infinity in theory. And you need a magnitude here. I'll put x of I. Who invented this series? He's a French guy. I should have put it on my list of famous people for you. This came from one of the guys named Fourier. I say one of the guys because there was a family of French people called Fourier. Several of them were famous mathematicians. Now in math, there's a lot of things named Fourier, but they're not all named for the same Fourier. So I don't know which one this one's named for. Okay. But what he showed is that you can take any random signal like this, and you can turn it into a bunch of individual sine waves, just a regular sine wave. This term right here, one of these, is a perfect sine. It has the frequency of omega I, and it has a size. The size is x of I. So from one road to another road, the only thing that changes is where are the big x of i's and where are the small x of i's. Okay? So in this experiment, you put a motion on here that's equal to a sine, and it's got some variable frequency, omega. And then you draw a graph. And the graph shows the force versus omega. Okay? If this graph looks something like this, what does that tell you about driving down the road? It tells me if I drive down a road where the Fourier series of what I encounter, these bumps, has a low frequency down in this range, then this suspension system is going to get very little force into the car. It will be a very smooth ride, I won't even notice. Or if it's a really high frequency, same thing, a really smooth ride. But if I happen to drive down a road that has this frequency, I'm going to feel it. I'm going to have a sore butt by the time I get home. Okay? Not good. My wife is going to yell at me if she's in the car. If she's driving the car and I'm sitting in it, she's going to try to find that frequency. Okay, so what's the idea of an active suspension? The idea of active suspension is, instead of having these two things fixed, to replace this with a single hydraulic cylinder, and it has a valve, and you can control the valve so that you control the pressure in that cylinder. The effect of controlling that pressure on this experiment is that you change where this peak is. So maybe one time it's over here, the next time it's over here, because you change something about that valve. Another time it's over here. On the active suspension, you measure this distance constantly, over and over again, numerical differentiate that distance, figure out the current velocity, the current measurement of the position. From those, you make this calculation. From that, you figure out which one of these frequencies is the one that's going to hurt your butt. And then you control that valve so that you shift this curve, and it does it about 50 times per second. By the time the wheel hits this bump, and the wheel starts up, it's already adjusting the valve so that you won't feel it in your butt. Okay, it's amazing. It was first invented by, I think Porsche, I'm not sure, but more and more car manufacturers are putting this in. It's not critical that you understand what an active suspension is right now. The point that I'm making is, the engineers that figure this out, for every single car, when they go to figure this out, they need to figure out how quick does this need to react? Right? How quick does this reaction have to be to make this adjustment? From the speed of that reaction, they then know how quickly they need to get a differential, calculate the derivative, and from that they decide what process they're going to use to calculate. Okay? Maybe that's enough examples. Well, one common thing to do is calculate this through the whole data range, maybe 10 times using different delta t's. And if you always get the same derivatives or something very close to the same derivative, then you assume it must be right. 10 different ways shouldn't calculate the same way. So if I start with the delta t, let's say of 0.1, try 0.01. Try 1. Try 0.001. Okay, now that's a range of 1 to 1,000, from 1 to 0.001. That's a big range. If all of those calculations give me about the same derivatives, I'm probably okay. What if they don't give me the same derivatives? That's where it gets trickier and trickier. Generally speaking, the smaller that you make delta t, the more wild kind of variation you're going to see in the derivative, no matter what. So it might be a good idea if you're going to make a small delta t to take average derivatives and see if the average smooths out a little bit. Okay? Okay. Good. So let's talk some more. So that's about section 4.7. 4.6, I just want to remind you, 4.6 was all about group finding. I think they're great examples of programming, but I don't think it's anything you need to worry about because everybody in the world is worried about group finding. So there's already a lot of good programs out there. You probably don't need to write your own. And there's even one in Excel. It's called GoalSeek. So you can take a look at that if you want. Goal sounds like a soccer game. GoalSeek. Sounds like football. It's in Excel under probably under tools or someplace. I don't know where exactly. Maybe it's not in every version. Yeah, check that. Do you have the lecture in front of you? Can you open 4.6 or maybe Alex could open it? While he's looking for that, I want to mention one other thing about Excel. It has something called macros. Have any of you used those? Yeah, it's kind of an interesting idea. Macros, the S is for plural. Macro would be a single. So this is something sort of like a program. I'm not going to put equal signs. It's not exactly the same thing, but it actually functions very similar to a program. The way it works in Excel is there's something like an on switch, and it's like turning on a tape recorder. Okay? Then you can put in as many Excel commands as you want. Keep doing whatever you want to do. You can do it for the next 6 years. Or 30 seconds, or 10 minutes, whatever. It could have 2 commands, it could have 1,000,000 commands. But when you're done with the sequence of commands that you wanted to remember, then you can turn it off. You can give these 2 things, this recording, it's one recording, right? Some name. And that becomes a new command in Excel. And whenever you call that name, it will just repeat whatever you did while you had the recorder turned on. Okay? So let's say you're doing some Excel operations, and it requires you to click 15 different things. So you can turn it on, record those 15 clicks, turn it off, and then every time you want to do it, you just type this name and you'll get those same 15. Okay? Say that again. Yeah, it's, I think functionally, for you as the user, it's a lot easier than C++, because you don't have to write out all the commands, right? Most of the commands that you're using in Excel, you're probably just going to pull off the menu anyway. So you can make up your own new menu name as a combination of all these other names that already exist in Excel. That's pretty handy for you. That's the good news. The bad news is Excel still has a limited number of math functions compared to C++. So there's still a limit as to exactly what we can do with this, but that would do some things. Did you mind it, Alex? Okay, yeah, so here's an idea of doing macro. So see, it even uses the word record. Record macro. So this is under tools, then you open macro, then record new macro. You have to give it a name right here. You can give it a shortcut key if you want. So all the shortcut keys are control and then another key. So you can call yours, this example uses control S. You can tell it where to store it. He's storing it inside this workflow. So it wouldn't be available in another workflow. But you could store it somewhere else if you want, in a more global location, so that you can use it over and over again. Oops, right. And then you can write your own description. So this is like a comment. And again, I can't say it enough. I think you should be very, very generous with your comments. So when you come back in a week or a year or 10 years and you wonder, what the heck was I doing? You have a description right there to remind you. So then you enter the same keystrokes, whatever ones you want, to do the process that you were doing. And to stop the recording, you can go back to the Tools menu and do macro, or there's an off button. It's blue. It will appear on the screen. Okay? That's pretty slick. So this is an example where he's finding roots using goal seek. He's finding the roots of a polynomial using goal seek. So first he just does it manually, finds the roots. Then he creates a macro to do it, and he runs the macro to do it. So I think that's a very good example for you to look at. Make sure that you understand how that works. Okay. That's 4.6. 4.8 is the first part of numerical integration. We talked about it before. Basically, all numerical integration has the same underlying theory, which is that you calculate the value of the function, and then you multiply it by the width of the step size, and that gives you the area of the little piece. Right? And an integral is equal to the sum of the area, so you add up all those little pieces and it gives you the total area. That's equal to the integral. So all numerical integration is approximately the same concept. Okay? Anybody have any questions about it? Then 4.9. Euler's method. This is for solving a first order differential equation. Okay? So if you had something like dx dt is equal to e to the x, what's the solution to this differential equation? The key point here is that we don't know what s is. So human beings have figured out solutions of differential equations like this in some cases, a lot of which are very important cases in science and engineering, but they haven't figured this out for all cases. So if you have a problem like this and you're trying to figure out what is x, if it's one of the cases that human beings have already solved, you can get the analytical solution, right? And just write out what x is. But if you can't figure that out, Euler's method is the method to try to solve for this numerically. And the idea is really easy. The next value is equal to the old value plus the rate of change times step size. So that's the basis of Euler's method. Let me draw a picture. If I have, say, x. Now remember, normally we don't know what the function x is. We're trying to figure that out. But let's say that it looks something like this. Okay, we know some value of starting point. Call this, say, t0. I know the value of x at t0. To get the value of x at t1, I use this basic logic. So this would tell me that x at t1 is equal to x at t0 plus the rate of change of x with respect to t change of x at the value of t0 times the step size, which would be t1 minus t0. If I have the equation for the derivative, and I'm trying to solve the differential equation, but I don't know how to do it in closed form, this equation is a numerical way of doing it, right? So this says, start at the value of x of t0, start right there, figure out the rate of change at that value. That would be the slope right here. Right, that's dx dt at t0. Multiply that slope by this distance, and that would predict that new value. That predicts the change. Very simple idea. Okay? So that's section 4.9. In my opinion, this is one of those super important sections because it's very common to solve dynamics problems. You're really interested in dynamics. And it's also very common to get a dynamics problem that you can't find a closed form solution for. Okay, because it's too complicated. People don't know. So I'll give you an example. I work a lot with satellites. In a satellite problem, we've got one mass and, say, another mass flying around. And they pull on each other with a gravity force. And this is proportional to the total mass times the distance cubed. So the distance in between them goes as a cube. So if I want to calculate how these two are going to move, the force is proportional to r cubed. And the motion would be something like r double dot, right? This is r, this vector. So r double dot is proportional to r cubed. That doesn't sound so hard, but humans knew that this was the basic law since Newton. And it was solved in the 1950s for two masses. Right? How many masses are flying around in the universe? Yeah, there are more stars in the Milky Way galaxy alone than there are grains of sand on all the beaches in the Earth. So it's never two bodies. There's always more. Another mass over here, say M3. This one is also pulling. Out here is M7, whatever. There's millions of them, and they're all pulling. Well, one step up from the two-body problem would have three bodies in it. So let's say we're sending a spacecraft to the moon. You've got the mass of the Earth. That's obviously a problem. The mass of the sun is obviously a problem. And the mass of the moon is obviously a problem. There's 3 of them out there, plus the spacecraft. There's 4 of them. Nobody knows how to calculate that solution in closed form. Yeah, it's 2011. We still don't know how to do that. So how did we get a spacecraft to land on the moon and come back? We used something like Euler's method to solve those equations. Okay, so in my opinion, this is one of the most important sections of the whole course for mechanical engineering students, because we love stuff that moves. Right? We love cars, boats, trains, airplanes, spacecraft. That's our thing. Robots, and all of those are dynamics problems, so they all have differential equations. What order are most of those differential equations? This is the basic law that works for most of them, right? And this is like second order, right? And Euler's method tells us how to do first order. Okay, so now I'm going to show you how to do a second order using first order. Convert higher order differential equation to first order. Yeah, we'll tune it up there. This is called state space. So I'm just going to do it by example. So let's say that I have something like m times d squared x dt squared plus, what symbol did you use for the damper in 208? C? Okay, I'm sure you used M for mass. If you had, did you work a problem that looks something like this? Did you do a problem something like that? You bet F. Okay, what did you label this guy? K? Okay, and what did you label this one? You didn't have that one? It's supposed to be friction. Maybe you put friction in here. With a mu, something like that? Okay, let's use mu. So plus mu x dx dt plus kx is equal to f of t. So there's the differential equation. It's second order. Euler's method works for first order. How can I use Euler's method on this? I'm going to define 2 new variables. I'll just call them z. There's no magic about the name. z1 is equal to x, and z2 is equal to dx dt. Okay? Now I have dc1 dt is equal to z2 dc2 dt is equal to 1 over m times minus mu z2 minus k z1 plus f of t. So I went from 1 second order down to 2 first order. Okay? Now the idea would be to use Euler's method, the same basic idea. Use Euler's method on these 2 equations at the same time. Alright? The other day I pointed out that if you add one more mass, like I already erased it, if you add another mass, you would have a 4th order differential equation. Second order for the first mass, second order for the second mass, 4th order. When you convert to first order, in that case, you would have 4 of these. There would be 4 Z's, and then it would look like 4 of these, but it's the same process. It's very straightforward. And then you can use Euler's method on all of them. And that's how you can solve as big a dynamics problem as you want. That's how you can send a spacecraft to the moon. That's how you can take off in Hanoi and land in London where you're supposed to, and not in the middle of the ocean or someplace where you're not supposed to, because you can calculate correctly what the solution of the differential equation is. Okay? This is how you can calculate what's going to happen in the next half of a second or so when my wheel of my car hits a bump. And that way I can send a signal back to that hydraulic cylinder and change the valve so I don't even feel the bump. The car's feeling it. The tire could already be moving. But this calculation can happen so fast it solves the differential equation. Because remember, it looks like a mass with a spring and a damper. It solves the differential equation, figures out what's going to happen to the car, changes the calculation by putting a new valve in. You don't feel it. There are ships that have automatic wings under the water. When they're going through a really rough storm, like a typhoon, huge waves hit the ship. Under the water, acting like airplane wings, there are panels that anticipate that motion. As the water starts to rise, the ship's really heavy. It doesn't go up immediately. They can feel the beginning of the water adjust their shape and help the ship to stay more level. So the people on board maybe they can eat their lunch and not get sick. Okay? In airplanes, same thing. When it hits turbulence, there's adjustments that are made automatically. All airplanes now are fly-by-wire, as I mentioned, the modern jets. So the pilot sits in the cockpit, he moves the stick, he thinks he's really controlling something. He's not. He's playing a video game. He's playing a video game where he tells the airplane, if I move the stick like this, I hope you go that way. Right? Then there's a computer inside that's measuring everything that's going on in the airplane and making that calculation and solving a whole bunch of differential equations. Because this dynamics predicts what's going to happen in the future. It does that instantaneously, nearly instantaneously. And then it adjusts the surface on the plane. It changes the engine, it changes the wings, so you get a nice smooth turn. Maybe the pilot is kind of an idiot. He's actually doing this. The computer will smooth all that out and give it a nice smooth turn, whatever they think he's trying to do. Right? Okay, cool. All right, so there's an example in here. When you use Euler's method, you have the same problem as you have with numerical differentiation. And that is to decide this guy. You have to decide how far is the next point going to be, the next point, the next point. Again, the theory says pick them as close together as possible. If you pick them close together, the rate of change will be more accurate for a long time. So if the function is doing something like this, if I pick points that are right beside each other, then the prediction of the next point should be more accurate. If I pick points that are far apart, like say these two, well that's not bad actually, but if I pick these two, the slope out here is something like this. So the predicted value would be up here. Because it uses the rate of change as a slope times the step size. Here's the step size. And the right answer is down here. It didn't get it right. That step size is obviously too big. But if you pick one that's really small, you have to make a whole lot of steps. And every step is not going to be perfect. The more steps you make, you accumulate error as you go along. So what's the right number of steps? So this gives you an example where he did a simple equation. This was the differential equation up here. So here's the slope, x plus 5y. There's the slope part. That's this term, rate of change. Here's the beginning value, y1. This is the new value, the next value. That's y at x plus delta x, and that's the step size delta x. So you use this equation. What happens if you change the size of delta x, which is the right one? So here's a table where he used 0.01. At the end of the integral, he had 136.5. Here he used 0.001, he got 152.2. That's a pretty big difference. Right? That's 10%. Now, some problems, you would be so happy to have only 10% difference. Now it's time to pop here. But sometimes 10% difference is too huge. You could possibly imagine that that's the right answer. So he tries another one. This one gives almost the same answer as that one. Which one is right? You don't know. You don't know. But hopefully, if you try a bunch of different step sizes, and a lot of them give about the same answer, probably that's right. That might be the best you can do. Okay? If you knew what the right answer is, you would just solve this equation. You wouldn't bother to do this numerical integration. The point is that you don't know the right answer. So you calculate over and over again. Hopefully, you'll see some consistency out here. And if you see some consistency, you have a little more confidence that, yeah, this is probably right. Okay? It's good stuff. If you can get a handle on this concept, I think that this is going to sound. This is not all my colleagues would agree with. Most of my colleagues don't know about the people in dynamics, which is obviously the most important part of mechanical engineering, would say that knowing how to do this is probably half of all the important things to know about mechanical engineering. Because we love stuff that moves. We love stuff that moves, and if it moves, the model for it, the mathematical model, is a differential equation. Period. So you have to be able to solve differential equations. And a lot of the really interesting things that move have a model that's a differential equation that human beings have not figured out with a closed form solution. So your only chance to solve it is to do it numerically. You have to be able to do it. Okay. Okay, any questions about this? All right, in my opinion is not always the same as yours, I know. In my opinion, we're down to chapter 4. So why don't we, let's go ahead and go through this. Is this still 4.9? Let's go through 4.9 slide by slide, and then just step by steps. This is 4.9, I think, right? Yeah, let's do this one, because this is the last one in chapter 4. Is there anybody that doesn't understand the issue of selecting the step size? The step size that you pick will usually change your answer at least a little bit. Which one is right? You can't know. There's no way to know. That's why people build a test model, and first they put a crash dummy in it, or maybe a monkey or something like that. Or if some really brave person gets inside, but the first try is always, gee, did I make that calculation right? There's no way to know ahead of time. But just to repeat, one thing you can do to help raise your confidence, try a lot of different step sizes. And if most of them give you about the same answer, there's a good chance it's the right answer. But you still can't prove it. There's still a little bit of faith going on. Okay, let's go ahead and move back to number 1. Let's start at the top. So pause for a second. Okay, any questions about the basic concept? This is the concept. So again, the next value, the one we're going to calculate, is based on the current value, and it's assumed that at the very beginning of the whole process, we have a piece of data or something that tells us where to start. After we start, though, every new value is calculated from an old value, and there's no way to prove that they're correct anymore. You just hope that it's working. You use the derivative and a step size, and you control the step size. So you run this process. The normal thing is to run this process using some step size, see what you calculate. Then do it again with a different step size. See what you calculate. Do it again and again, maybe 10 times, maybe 1,000, maybe 2. I mean, it's up to you. It's art. It's not science anymore. And compare those answers. If they all look about the same, you probably have the right answer. If they don't look the same, you're probably not going to be able to figure out the right answer. You'll never know which one's right. Okay. So this is what it looks like with the derivatives. And here's the basic equation using the derivative. There's the derivative. Can we back up just a second? All right, so I said you could convert to state space. In state space, this equation looks exactly the same, but there is a little bit of a difference, which is this would be a vector. So I don't know if I still have it there. I guess, yeah. So I'm doing two z's at the same time. So this is a vector that's 2 by 1. This is a vector 2 by 1. Step size is a vector. The derivatives is a matrix. It's the right size of the matrix to multiply the steps that I need in order to make this 2 by 1. If I have two masses, this is 4 by 1. This is 4 by 1. This is a matrix of derivatives, so that the product of that times the step size is a 4 by 1 correction. Okay? You want to know what the biggest one I've ever done? This one was really fun. On the U.S. Space Shuttle, the Space Shuttle does a lot of experiments in space. So it flies out and it opens up bay doors. Again, I know it's hard to believe this is actually only a drawing, it's not a photograph. This is the Space Shuttle. And out of that bay, there was one set of experiments that used something called the MAST. I think it was an acronym, but I don't know what it stood for. But I think MAST were 4 words. The MAST was actually built in Canada, not the U.S. And the MAST was a big truss structure. Each bay, each one of these pieces of it was something like about 1.5 meters. Okay? And they all folded. They all had a little thing in the middle that they could fold in half. And the whole thing could fold down and sit in a pile that was about this high, about 1 meter high. When it was folded out, it would be a total of about 70 meters. And way out on the end of it, there was some science experiments. The experiments were 70 meters away from the space shuttle because they were so sensitive that the mass of the space shuttle would affect the experiment. So they had to be moved away. Okay? Now, the question was, how much motion is going to get transferred from the space shuttle through the mass out to that experiment? Like, maybe there's 6 astronauts out there. This guy's sleeping. But this guy's going to the bathroom. So he walks along, and every step he takes, listen, the thing's shaking a little bit. So here we have all this trouble. We went to all this trouble building this mini mast to put this thing out 70 meters away so it won't be affected. But this guy happens to be going to the bathroom, so this is shaking a little bit, and it ruins the experiment. So the question is, can we build this mast, and so the dynamics is such that it will isolate the motion here from the motion here? So it's an F equals ma problem. If there's something moving down here, what happens out here? It's a lot like the car problem, conceptually, the suspension of the car. The difference is, as far as these bays go, to get to 70 meters at 1.5, this is 50 approximately 50 of these. Each one was like a mass. So 50 masses put together. Each one has its own second order differential equation, F equals ma. When you build the model for this thing, it has about 100 words. So back over here, when I solve that, this is a vector. I guess I was pointing on this a minute ago. This is a vector that's 100 by 200 by 1. Because remember, each piece of each m has a second order differential equation, and each one of those requires 2 z's. So this is 200 long, this is 200 long. This is a huge matrix full of derivatives to turn the step size into the next solution. Okay? So that was 200. One of the projects I did with the car company, trying to figure out why the car was making noise. They were convinced that the noise was coming out of a door panel. So just the piece of sheet metal on the outside of the door. Here's the handle, the window's up here. That's just one big piece of metal. They treated this metal for the model as if it was made of a whole lot of little plates of metal. And each plate was modeled as if it was a single mass. And they used about 100,000. The grid was about 100,000 little plates of metal. So the differential equation was 200,000 order. And the state space here was 400,000. 400,000. Now this is really interesting to me. I worked on both of these projects. Okay? In this case, we're sending something that costs $1 billion out into space in one try. The model's 200. This is a door on a car. It's the outside panel of the door of the car. It's not even the engine. It's not even the suspension. 400,000 is the size of the model. Why? Because this is ultimately worth a lot more to the company. Because they want to make money. They want to get it right. They need to get rid of that noise. Okay, anyway, I just want to give some more examples of how these things can be really large. And in your career, I think you'll work on a lot of problems like that. Really big problems. Alright, so I think we looked at this. Was this the one we looked at before? Yeah, with the different sizes. So I think he's calculating this in, I think this calculation was done in Excel, but I'm not sure. Maybe it was done in C++. But he put in different sizes of the step size and saw what answer he got at 1. This is an integral that's going from 0 to 1. So when you use 0.01, it takes 100 steps. When you use 0.001, it takes 1,000 steps. 0,001, 10,000 steps. Right? So it's this trade-off, because the accuracy of each step should be better if the size is small. But you have to make a lot more steps. So the little bit of error accumulates because there's more steps. So what's the right answer? You don't know. But it turns out here, these two give approximately the same answer. So the right answer is probably about 153. That probably is the right answer. This one is probably not the right answer. But you don't know. Okay? So this is just another example of a first order equation. Okay, we need to really just spend much time on this. Maybe pause for a second, Alex. I'll just mention one more physical reason you mentioned this. Why would you need to solve this equation numerically? Yeah, this equation you definitely can solve in the closed form. That's easy. But it may be that the value of k is some very odd function that you can't forget. But if k is a constant, the solution to that equation is easy. What's the solution to that differential equation if k is constant? This is one humans do know. Minus a times x. That's that equation. Right? If k is constant, what's the solution? And if this K had a negative value, here's another case where the numerical integration may give you some trouble. Right? If K has a positive value, let's say you didn't know this was a solution. So you start calculating this integral. Start calculating this differential equation. If K is negative, the solution is going to do this. So as you put in your step size, depending on how far you go, the difference in magnitude from where you start up here, this could be such a big number that remember the problem with precision only stores a certain number of significant figures, maybe 6, or if you're double, it's 12 figures. If you're adding bigger and bigger and bigger numbers, eventually the effect of this n is lost, right? Because of the precision. It's that same thing we talked about before. 10 million plus 1 minus 10 million. It's not 0. I mean, it's not 1. Right? It's 0. So if this range got really big, you would have that same problem. Okay. Yeah, here's the closed form solution. There's Euler's equation. And so he calculates it a couple of ways, and that's what he gets. So this is an example where he does know the exact solution, so he calculates it, the blue, and then Euler's for this step size. I don't know what step size he's using, 20 it looks like. Euler starts to get a little bit of an error, right? So you can play around with the step size and see if you can make Euler's more accurate. Okay, next. Yeah, this is his suggestion for trident codes, correct accuracy. Number 1 is a nice idea, but in my career, I haven't found that it happens very often if you do this. Okay, so number 1 says, simplify the problem to something you really can solve analytically. Then play with the step size for that problem until you get a really good solution. Then go back to the one that's the real problem you're trying to solve and use that same step size. That's not a bad idea, but there's no way to guarantee again, because the problem that you're actually comparing with is not the same one that you're going to solve. So just because the step size works well on this one, doesn't mean it's necessarily going to work well on the one you are trying to solve. So I'm not sure that's a good idea. And then, yeah, this is the second part of that one. I'm not crazy about this. I think the better idea is just do the integration several times using different step sizes, and if most of them give you about the right answer, it's probably the right answer. And if most of them don't give you the same answer, then you're probably not going to get the right answer. You have no way of knowing if any of them are right. Okay. Okay, let's talk about how we're going to handle the problems that we're going to turn in. Because it's a little confusing. I originally thought that maybe you could just email them to me, but that's not turning out to be very reliable. Hopefully we'll get that fixed, but ideally I would like for you to be emailing me executable versions of the things that you're preparing, and then I'll just put them into my computer and run them. Maybe not even more for you, I figure if you're sending me viruses. Yeah, please scan your files before you send them to me. Scan them for virus, yeah. So I think for now, I will be optimistic that they're going to fix the email, and so I'll be able to start receiving it again. I don't have any internet access. But assuming I get it, then I want you to email me. So you should have, why don't you start emailing me the solutions for the homework number 2, right? Those are the chapter 2 problems. Homework number 3, projects from chapter 2. Yeah, the projects from chapter 3. This 4 will delay for now. But why don't you send me the things for 2 and 3? No project for chapter 3? Okay, so that's an easy one. Yeah. Well, if there's no project, you don't have to do it. So. I can make one up for you. What? You could always try doing any of the assignments in C that are given for C++. You could try doing those in Excel just to figure that out. Because if you could do it in Excel, that would be great practice. And you know, most people think that, including me, think that C++ has a greater math capability in solving more complicated problems. Excel is easy to use, but usually you can't use it because it's not advanced enough. So if you could figure out how to solve the C++ problems using Excel, that would be pretty good. But I know you have a few other things to do. Maybe that's something to do next month, after this is all done. Okay, so chapter 2, homework. I'd like you to email me as soon as possible. Chapter 3, homework, as soon as possible. Chapter 3, project, as soon as possible. And there is no chapter 2 project. So that, I'm sorry, chapter 2 project as soon as possible, no chapter 2 project. So that will leave 4 things. You can look forward and you know what's coming. 4 things will be left. Chapter 4 homework, Chapter 4 project, Chapter 5 homework, Chapter 5 project. 4 things, 1 week. So I'm going to be sort of flexible about when you turn them in, but we're obviously running out of time. And yesterday, Mrs. Ha asked me to do something on Friday I didn't know about. So I think that we can't have class on Friday. So why don't we, I don't know, do you want to have another class tomorrow morning? Yeah, we're not going to, the engineering solutions class, whatever it's called, engineering principles, doesn't meet in the morning. I invited people to come at 10 o'clock to answer questions, so we could take a break at 10 for those questions. But in the meantime, we can have this class